I was actually hoping that maybe people could introduce themselves, just because I don't think I know everyone, and it would be useful just to know a little bit about what the audience's background is.
Yeah, I was going to say actually, also, yeah, I don't have any sort of background in formal verification. So, yeah, I'll start. I'm a PhD student at CISPA. So I'm working under Antoine Joux, mostly working on cryptanalysis. At the moment, I'm just a first year, but I'm focusing on well, index calculus methods and basically num-field sieve and approaches to attacking, yeah, mostly attacking DLP. So yeah, that's my background.
Great, and we have a fond attachment to everyone from CISPA because you guys keep sending us excellent visiting faculty. So
yeah. So I've looked at this as well. There's a sort of a postdoc track as well with Stanford, which is kind of cool.
Yeah, totally. Anyone else willing to introduce themselves and tell me a little bit about your background?
Hey everyone, I'm Lance. I'm a REST developer. I really like staying abreast with new research in the Delendum group. So just like joining these calls to learn more.
Got you.
Oh, I can't hear you now, Ulrich.
But I think it's because they're muted.
Oh yeah.
Now it should work. So essentially Starks, Snarks, that's my realm.
Gotcha.
So in short. So no formal verification at all.
Cool. Okay, I think this is actually good. This is like, and then I know Ventali's background is ZK as well. So this is good. So it sounds like our audience knows some stuff about crypto, maybe about ZK, less about verification, and that's great. We can work with that. So I'll go ahead and share my screen. I have some slides. There aren't too many of them, so we'll see how long it actually takes us to go through them. Yeah, okay, so today, I guess I should introduce myself as well. My name is Alex. I am a PhD student at Stanford. Most of my research is related to cryptography, verification, compilers. And today specifically, we're going to talk about what is at its core a cryptography and a verification project, really a verification project related to cryptography. What we did, or what we're doing, is incorporating finite field reasoning into an SMT solver. So an SMT solver is a kind of tool that's used to do automated verification. It's like the baseline reasoning technology that the verifier is built on. And our goal was to teach an SMT solver to understand finite fields so that you could apply SMT solvers to things like zero-knowledge proofs, systems based on them, perhaps even other kinds of crypto systems that have algebraic definitions. And so actually what I want to start by is discussing slightly more in slightly more detail what like the pipeline that we're imagining is and why that pipeline needs verification. So the pipeline that we're imagining here is the classic pipeline for zero knowledge, for using a zero knowledge proof, which is that you've got some high level idea for a private application. You want to turn that into an actual private application. Perhaps you're building a private cryptocurrency. And a zero knowledge proof is a key part of what allows you to do this, but it's not the only thing. Because you see, the way that the zero knowledge proof works is what you have to give it is a algebraic constraint system, a set of equations in a finite field. You can think of these as integer equations that hold modulo prime p. Perhaps these equations define some kind of arithmetic circuit, perhaps in some arithmetization like Planckish or R1CS. We're not going to care so much about the exact format of these equations. For our purposes, we're just thinking about, we're just going to treat all these equations as some kind of system of field equations. And once you've taken your high level idea and you've expressed it as these equations, then a zero knowledge proof can give you a prover and a verifier, and you can go ahead and build your privacy preserving application. But the task of coming up with the equations, that is incumbent upon you. So you have to through some kind of programming process, probably with the assistance of a synthesis library or of some kind of compiler, you're going to be translating your idea into these equations. And when you think about the two parts of this pipeline, the programming process and then the zero knowledge proof, the zero knowledge proof was written once and it's being applied very automatically here. The programming process, that's specific to your application. And so when you think about that, it seems clear that the programming process is the process that we should be more concerned about finding bugs in. Because anytime that humans try to take some particular idea and express it formally in any language, they make mistakes. And of course, the question is, what are the consequences of mistakes in the context of building some kind of privacy preserving system like a private cryptocurrency? Well, those consequences, they can be very severe. It's totally reasonable to imagine that missing a single equation in the definition of, for example, Zcash would render the currency insolvent by allowing somebody to spend money that they're not authorized to spend, or by allowing them to spend the same money twice, or by allowing them to just print money out of thin air. So it's really easy to imagine that missing even one equation could totally compromise the integrity of the system. And perhaps even more concerningly, it's very likely that such a bug wouldn't actually compromise the privacy of the system. It wouldn't, the zero knowledge property would still hold. And so if someone was careful about how they exploited the bug, there's no way, or it would be very hard for you to ever tell that they had found such a bug or that they were exploiting it. So the kind of insolvency that's caused by these bugs isn't just insolvency. It's like a kind of covert insolvency. As long as someone doesn't spend too much money, flies under the radar, you're never going to know. And so, the possibility for this kind of covert insolvency, even if it doesn't exist, is obviously a huge liability for any system of this kind. And so the natural question is whether or not we can verify that there are no bugs, whether we can verify that that the high-level idea has been accurately encoded as field equations. And this is a hard problem. Verification is always hard, but this problem is extra hard because of the difference between the spec and the implementation. You see, if we were to write down a spec for a payment system, that spec would deal with objects that we're familiar with. There might be some Boolean reasoning indicating when somebody can spend money. There might be some fixed size integers that indicate how much money somebody has to spend. There might be arrays that represent the global state of the system, the account balance for every individual. All of these objects are objects that have been, the object of verification for a long time. And so existing solvers, things like SMT solvers, can reason about Booleans, about fixed size integers, about arrays with reasonable efficacy. But the implementation here in the context of these zero knowledge proof systems is a set of finite field equations. And finite field equations are not something that SMT solvers can reason about, at least not prior to this work. And so if you wanted to do verification, automated verification related to zero knowledge proofs, to these field equations, then you'd have to represent those equations in some other way. I said earlier that, at least for the purposes of this talk, a finite field is the integers modulo prime. So you could try to do integer reasoning with an explicit modulus computation. You could even do fixed size integer reasoning with an explicit modulus computation, because all the numbers are less than p or less than 2p or p squared or something like that. But both of these approaches end up not doing so well, which is not so surprising. Like, somehow, since this seems like the wrong thing, what we really want is some way of reasoning directly about the field, and that's exactly what we've been working on recently, and that's what I'm here to tell you about today. So yeah, our goal is to add finite field, or what we have done, I guess now at this point, is adding finite field reasoning to an SMT solver. So that means that we define a language for field constraints. In SMT terms, this is called a theory. We give a number of verification problems related to zero knowledge proofs that are expressed in this language. I'll touch on those later. We build what's called a decision procedure into the SMT solver. This is something that allows the SMT solver to solve formulas that involve field constraints. Our decision procedure, in some ways, is very much based on classic computer algebra, nothing new to see here. But importantly, it also avoids some classic ideas from computer algebra called field polynomials that would be totally disastrous, as you will see later in the talk. And then finally, we take CVC5, which is the SMT solver that we build here at Stanford, and we code up all of our ideas inside CVC5 and show that with our decision procedure, CVC5 can solve the kinds of verification problems that we're looking at far more effectively than any of the pre-existing approaches. So that's kind of the scope here. Zooming out a bit, if you think about verification as some kind of house that we're hoping to build, we're not building the house yet. We're working on the foundation, which is the solver technology. And the reason that I'm here to tell you guys about this stuff is that we think that this foundation is pretty flexible and will be more broadly useful. And so we want as many people to know about it as possible. That said, if there's time at the end, I do have a few slides about one of the verification projects that we've been doing with this solver. So this is a verification project where we open up a ZKP compiler. We look at a particular component in the compiler and we verify that component, or at least partially verify that component using the solver. And also, I should say, we don't actually verify the component. We find some bugs in it, and we fix the bugs, and then we verify the fixed component. So yeah, so this stuff is useful, helps you find real bugs. Okay, so this is the scope. I guess we'll jump into it then. Yeah, okay. Actually, so there's a question from Lance. Are we talking about NP hard or just difficult? Yeah, so the table stakes in verification are always NP hard or harder. And indeed, solving field equations is NP hard. Yeah. And how do you know that? Because you can encode sat in it, so that's why it's NP hard. It's also NP complete, and the reason for that is that the space is finite. So the solution is a source is in the case that it's sat, the solution is a short proof. Cool. Yeah, although I encourage people to actually yell out questions because it's kind of hard for me to see chat. So yeah. So yeah, in the future, try to ask the questions verbally. Okay, so let's charge ahead. So first thing, what are the kinds of equations that we're trying to solve? For the purposes of this talk, we're going to be focusing on finite fields of prime order, although the ideas are general. So a finite field of prime order, we write z sub p. This is the integers mod p. So the set of objects that you have is 0 through p minus 1. The operations that you can do are addition, multiplication, and equalities, all mod p. And for the purposes of the work that we're doing, we always assume that p is fixed and known in advance. So when you ask a question of the solver, you say what p is. P is not a variable. And this is like very acceptable in the context of a zero knowledge proof, because in the context of a zero knowledge proof, the proof system has fixed what the prime is already. So just as a warm up, we'll look at a few equations modulo p. So here I've got one. So this is a formula, x equals x plus 1 or y squared equals y. So this is a formula, it might be true, it might be satisfiable or unsatisfiable. This formula is actually satisfiable. The reason is that if you set y equal to 0, then indeed 0 squared is equal to 0. So the second equation is true. And if the second equation is true, we don't care about the first equation. So you can set x to anything you want. So we'd like a solver that could tell us that this is satisfiable and give us, for example, x equals 0, y equals 0 as a solution. On the other hand, if our formula was just a single equation, x equals x plus 1, this is actually unsatisfiable. In any field, but in particular in the integers mod 3, for example. And the reason is nothing is equal to itself plus 1. We'd like our solver to be able to determine this as well. So these are some basic formulas. What are the actual formulas that we'd like to be able to solve? Well, the actual formulas are related to zero knowledge proofs. In particular, they're related to field equations that encode some other kind of computation. And the benchmarks that we used while we were developing our solver are all related to equations that are supposed to encode Boolean functions. And so let's think about what it means for a system of equations to encode a Boolean function. We'll let our Boolean function be called f. It has inputs zi, and it has a single output z. For example, f might be a conjunction of 3 inputs. So it might be z equals z0 and z1 and z2. Our system of field equations we'll call phi prime. And we'll assume that system of field equations includes a variable zi prime that represents each zi. So this variable is going to be set to 1 when zi is true and 0 when zi is false. We'll also assume that there's some distinguished variable z prime that is supposed to be the output of the function. So it's supposed to be 1 when the Boolean function's output is true and 0 otherwise. And then, of course, there might be lots of other variables in the system of field equations, perhaps encoding intermediate values in the function, perhaps doing other stuff. And so our question is what does it mean for z prime to for phi prime to accurately represent f? And I'll show you just one of the conditions that we write down that checks for this. And so this is the soundness condition. So we say that phi prime is a sound representation of f if the following formula is valid. So if the following is always true. So here I have the condition, but we'll break it down piece by piece. What this says is that, first of all, if I have some assignment where the equations hold, so I have some way of solving the system of field equations, and in this solution to the system of field equations, all of the input field variables, the zi primes, are accurate encodings of the Boolean inputs. So ITE here it's an if then else expression. So we're saying Zi prime is 1 if Zi is true and 0 otherwise. So if I've solved the field equations and all of my inputs are accurate encodings of the Boolean inputs, then the field output should be an accurate encoding of the Boolean output. That's the condition. We want this to always be true. So essentially, we're saying it's impossible to solve the field equations without accurately evaluating the function. And yeah, so this is something that we would want. This is a formula that we'd want to feed into the solver, and we'd want to ask the solver, are there any counterexamples? And for example, if you set Z prime equal to Z prime 0 times Z prime 1 times Z prime 2, this is a very simple system of field equations that is a sound encoding of a conjunction. But for more complex Boolean functions, compilers produce very optimized and somewhat garbled system of field equations, and it's not actually obvious whether or not this condition is true. So this is the kind of condition that we want to check. Our benchmark set is basically just it's full of formulas of this form. So the way that we generate the benchmarks, we start by sampling a random Boolean formula. We encode that formula in some kind of programming language that we then feed into a zero-knowledge proof compiler, something like Socrates. That spits out a system of field equations. We identify what the inputs and the outputs are by inspecting the compiler's output. We then do something very interesting. We consider dropping some of the equations that the compiler gave us. I'll come back to that in a second. And then we go ahead and we write down the formula that is the soundness condition. And then we express that formula as an SMT query. It's a logical formula, so you just you put it in the right format, and it's something that you can feed into an SMT solver. And then we ask an SMT solver whether or not that formula is valid. So why do we consider dropping some of the compiler's output? Well, for these benchmarks, we're testing very simple inputs to the compiler, just Boolean functions, nothing complicated at all. We expect the compilers are actually going to be correct on Boolean functions, but we want to make sure that we have some examples of incorrect systems of equations in our benchmark set. And so the way that we do that is we just drop some of the compiler's output. And it seems likely that if you just start dropping random equations from the compiler's output, your result will now be unsound. And indeed, that is the case. So by dropping stuff, we come up with formulas that are invalid, or also known as satisfiable, i.e. there is a counterexample.
Do you ever do the opposite and add equations?
We actually don't. That's a good thing. So yeah, you'd expect that if you add equations, then the formula would still be sound, although it might not be complete. But we didn't try that here. Yeah, it's a good question. I'm trying to juggle this panel. And then I should actually say a little bit about how we drop them. So for some of the benchmarks, we drop random equations, and we expect that will produce something that's satisfiable. But there are no guarantees. Like maybe the compiler has some redundancy in its output. For some of the benchmarks, we know a little bit about the compilers, and we know that if you drop the final equation, the result will always be satisfiable. So we also do that sometimes. So the final thing I want to say about these benchmarks is that in this context, because we're working with a zero-knowledge proof, P, the prime, has to be very big for security reasons. It has to be on the order of 2 to the 256 bits for most zero-knowledge proof systems. And so this will come back later. This is a very unusual regime to try to reason about field equations in. Most prior work hasn't really thought about fields that are finite but are this large. Okay, any other questions about the benchmarks before we move on to how we actually do the reasoning?
Yeah. So what's the reason why you don't consider smaller fields?
Yeah, so the reason is that most DKPs, at least the historical ones, work with very large fields, but it's true that some DKPs work with smaller fields. And like some Stark-based systems, they obtain soundness through other techniques, not enlarging the field. And I think, so these other kinds of systems, they're going to use fields on the order of 2 to the 32, 2 to the 64. Let's put a pin in fields of that size and come back to it in a few slides, or when we understand more completely like the ramifications of large fields.
Thanks.
Yeah, good question. Okay, so let's charge ahead, and then we'll return to this question of field size in a second. Okay, so I'm not going to go through all the details of how we do the reasoning, especially since this group doesn't have a background in verification, but I'll sort of sketch some of the core ideas. So what you should imagine is that there's some larger SMT solver, and it's processing a Boolean formula that has complex structure. But ultimately, in the course of solving this more complex formulas, we end up with a bunch of subproblems, and all these subproblems are just equations in a finite field. So we have a bunch of polynomials, Ti. These polynomials are all multivariate. So they have coefficients in the field. They're in some set of variables, x1, x2, x3, so on. And what we want to know is whether or not these polynomials can all be 0 at the same time, whether or not they have any common roots. And what I'll explain at a high level is how we solve that problem specifically. The first tool that we apply to solve this problem is something called a Grosvenor basis engine. It's a classic tool from computer algebra. It answers a particular algebraic question. It tells you whether or not the constant polynomial 1 is in some ideal. You might not know what a Grosvenor basis engine is. In fact, you probably don't. You probably don't know what an ideal is. That's fine. I'll tell you what you need to know. First, you should know that this Grosvenor basis computation that we do, it's somewhat expensive. In particular, its runtime, in the worst case, scales very poorly with the number of variables and with the degree of the polynomials, the degree of the equations. The second thing that you need to know is that if this Grosvenor basis engine succeeds, if it says that 1 is in this ideal, that means the system is unsatisfiable. But unfortunately, the converse does not hold. If 1 is not in this ideal, the system might still be unsatisfiable. And I can give you intuition for what's going on wrong here. Essentially, the Grosvenor basis engine is too smart. We've given it some polynomials in a particular field. So their coefficients are in ZP. But it's telling us whether or not there are any roots, any common roots over not ZP, but over any extension of it. So by, we're probably not so used to finite fields. Let's think about reals and complex numbers instead. We've given it a bunch of polynomials with real coefficients, and it's telling us whether or not there are any complex roots. And we don't actually care about complex roots. So in some sense, it's not solving the problem that we actually care about. And if you have this problem and you go through the computer algebra literature, it turns out there's actually a solution. There's an approach to getting the Grosvenor basis engine back on track. There's an approach to making the Grosvenor basis engine reason about just the field that you're working in. And that approach is called a field polynomial. It's a polynomial of form x to the p minus x, where p here is the size of your field, the modulus that you're working with. The interesting thing about field polynomials, the advantage of using them is that their only roots are in the base field. They don't have any complex roots. And so if you add these field polynomials to your system of equations, it doesn't change which base field solutions exist, but it eliminates all of the complex solutions. And so now the fact that the Grosvenor basis engine is also thinking about complex solutions, that doesn't matter anymore because you've ruled all those out. And suddenly the Grosvenor basis engine is a complete solution to your problem. So that's the advantage. And that's why people say that you should include field polynomials in your system. But there's also a really big disadvantage, and at least in our context. And the big disadvantage is that the degree of the field polynomials is, well, the prime p. And in our context, in the context of a zero-knowledge proof system, p is very big. For the systems that we were working with, it's on the order of 2 to the 255. But even with the other kinds of systems that I think it was Ulrich's question that Ulrich was alluding to, p is still pretty big. It's on the order of 2 to the 32, 2 to the 64. And when you look at the runtime of the Grosvenor basis engine and how it scales in the degree, for degrees of this size, even 2 to the 32, this is never going to work. The Grosvenor basis engine is not going to finish before the universe dies. So this idea of using field polynomials is just not acceptable. On the other hand, if your field is like the integers mod 2 or the integers mod 3, field polynomials can be a reasonable thing to do. So what do we do? Well, we don't include field polynomials. Instead, in the event that the Grosvenor basis engine claims that the system is satisfiable, we don't believe it, and we go into a kind of backtracking search that we designed just for this problem. This backtracking search, in the worst case, is worse than a Grosvenor basis engine, but it's better than a Grosvenor basis engine with field polynomials. It gives us a result that we can trust. And I'm not going to go all the way into it, but the big liability in this backtracking search is that in the worst case, its runtime depends on the field size. It doesn't depend on the field size to the 2 to the n, but it does depend on the field size, and that could be bad. But in practice, we see that the field solver doesn't seem to be exhibiting this worst case performance. So I want to walk you through some of the experiments that we did that show that worst case performance isn't being realized. So here, what I'm going to be showing you. Actually, maybe I should pause. Yeah, let's pause here in case we have any questions about the decision procedure. Okay.
Could you? Sorry. I only ran over the notion, the notion of Grosvenor basis in the cryptanalysis of let's say algebraic hashes.
Yeah.
Could you quickly just give me a hint? The connection with Grosvenor basis and the problem in question.
Totally. Yeah, so just like giving like one more layer of detail there. This ideal, this notation, angle brackets TI, that's the set of all linear combinations of the TI. So I'm imagining all the combinations, all the things that I can build by taking each TI, multiplying it by some polynomial, and adding up the results. And if I can find some linear combination of the input equations that is equal to a non-zero constant, such as 1, that means the system must be unsolvable. Because I know every individual TI is 0 if some linear combination, so any linear combination of them needs to be equal to 0. And if that linear combination is giving me 1, it means the system is unsolvable. And so that's why a Grosvenor basis engine is like a reasonable test for unsatisfiability. And unfortunately, for reasons I was alluding to, the fact that extension solutions can trick you, it's not a good test for satisfiability.
Yeah, and what's sorry, somebody else wanted to talk.
I can go after you.
Yeah, go ahead.
So my question is, why does it come with complex numbers? Does your Grosvenor basis solver has a base field? Because it shouldn't come with complex numbers if you set the base field.
Yeah. So yeah, the answer is like the Grosvenor bases on their own are just not complete over the base field. They're not. And so the classic algebraic technique for closing them over the base field, and perhaps you've interacted with some Grosvenor basis engine that's doing this automatically, is to add field polynomials. And unfortunately, that just doesn't work in our setting. Now, on the other hand, if I'm wrong and there's some other technique, I would love to know about it. But I'm not aware of such a technique. Yeah.
But
Okay.
maybe the confusion is that you use the term complex numbers. No, I don't know. Yeah, maybe that's.
Yeah. So that's reasoning by analogy. So actually, what's actually going on, we're working over a finite field. And so what we're worried about isn't the complex numbers. We're worried about extensions of our finite field.
Okay, so it's like the tower with
Exactly. Yes.
level. Okay, I see.
Yeah.
So just the last thing. So the ideal the Grosvenor basis test is talking about is it over an arbitrary extension field or the algebraic closure or something like it?
No. So the ideal is computed over polynomials with coefficients in the base field. But
so why the test for if it's. So I lost the connection with the base. Why it's not sufficient for base field?
Yeah. So the easiest way to see this is just with an example. So if my system of equations is just a single equation, x squared plus 1 equals 0. So x squared equals -1. That is unsatisfiable. For example, in the integers mod 3, there's no square root of -1 in Z3. But that ideal does not contain a constant. And it's easy to see why the ideal wouldn't contain a constant, because since I only have one polynomial, x squared plus 1, anything I multiply with this is just going to increase the power of x. And so I'm never going to end up with a constant.
Would you?
So
no, I don't want to hitchhike the session. So
no, it's a good question. Let me put
no,
this.
It's the same. I couldn't fully follow your thoughts. So maybe it's better if I try to explain my words. So
yeah.
Given this set of polynomials, so I agree. If one is in the ideal, it can't be satisfiable.
Yeah.
Where's the point? Maybe just repeat. Where's the point that the base field comes into? Because if the Grosvenor solver works over CP anyway, I didn't get the reason for the backtracking search for the other. Because
yeah, so I think the thing to realize is that the polynomial, like, it's good to think about an example. So like x squared plus 1 generates an ideal that doesn't contain. So I'm putting this in chat. So x squared plus 1 generates an ideal that doesn't contain 1. But it's actually, this polynomial has no roots, for example, in Z3. And I think the reason is like ideal membership and satisfiability, they're not actually equivalent. They're only equivalent in algebraically closed fields, and finite fields are not.
Okay, so, got it. That was missing. The link to the algebraic closed field.
Yeah. So, and this is like a slightly weirder statement, but you can also prove this. Like they are equivalent to module, like satisfiability over any extension is equivalent to this ideal membership problem, even over a non-closed field. But okay, so yeah, let's charge ahead, and we can come back and talk more about the algebra at the end if we want. So the experiments that we ran, I'm not going to show you them all, but I'll show you just maybe like 1 or 2 of them. And so in this experiment, I'm going to be showing a cactus plot. So that means on the x-axis, we try to solve more verification problems. This is checking that some system of equations encodes a Boolean function. On the y-axis, we look at how long it takes to solve those problems. And so you're hoping that your verification approach has points that are down and to the right, because that means that you're solving more verification problems in less time. There are a number of baselines that we can compare our system to. Most of these baselines are based on integer reasoning. So, this is a prime order finite field. You can model your equations as integer equations that explicitly hold modulo p, but this doesn't do so well. You can just with either arbitrary precision integers or fixed size integers. It kind of doesn't matter. None of these techniques do very well, and the reason is that just like understanding the modulus operation is not trivial. And yeah, and so the SMT solver tends to get stuck. Another thing that you might try to do is forget about SMT altogether and just try to turn this into a computer algebra problem. Throw something like Mathematica or just a standalone Grosvenor basis engine at it. This also doesn't do so well. And the reason that the computer algebra approaches don't do well is that our problem, it's got field equation, but it also has Boolean structure. We're trying to check whether some Boolean formula agrees with a system of field equations. And you can indeed embed the Boolean structure in terms of field operations and then ask a computer algebra system to try to understand it. But computer algebra systems are just not good SAT solvers, despite the best efforts of many people over many decades. There are other techniques that are better for understanding Booleans. So this approach also struggles. But in some sense, what you want to do, of course, is you want to try to bring the computer algebra style reasoning and satisfiability search together, and that's exactly what we're doing, and this ends up doing far better. So we can solve a lot more verification problems with this kind of combined approach. One other thing I want to touch on is what happens if we were to use field polynomials. And it turns out this just goes very badly. So here, what we're looking at is benchmarks that have an artificially small prime, a prime that's only like 4 to 12 bits. And what we're seeing is that already the field solver is much worse with field polynomials. So on the x-axis, we have how long it takes to solve problems with the field polynomials included. On the y-axis, we have our actual solver. And what we're seeing is that problems that the actual solver could handle in less than half a second sometimes takes the solver with field polynomials minutes to solve. And this is only for a prime of like 4 to 12 bits. We're not anything close to the 32 bits that things like Starks would use, or the 256 bits that the other kinds of ZKPs would use. And if you look at the breakdown of runtime based on the number of bits in P, then what you can see is that the field polynomial solver is going exponential, and we're never going to get to any reasonable number of bits. Okay, so that's just like a quick tour of the experiments. If you're curious, we talk about a lot more in the paper, of course. We consider other kinds of properties, not just soundness. We of course explain the decision procedure in full. And we do lots of experiments looking at how alternative strategies break down, and basically just showing that your intuition about why things like bit vector reasoning or field polynomials are bad, why we give sort of evidence that your intuition is correct for why those things are bad. There's a lot that we're still trying to do, but maybe I'll skip this for now and we can talk more about it later on. What I do want to say is I want to say a little bit about one example of how you can use this kind of SMT solver to do verification work related to ZKPs. And so that's what I'll explain now. So, our initial motivation was trying to verify that the compilation or programming process had been done correctly, that some idea agreed with equations. And our benchmarks actually focused on checking compilers, but they focused on checking compilers in a very limited way. We sampled random input functions to the compilers. We ran the compilers on those functions. We got field constraint systems as output, and then we checked that system of field equations was correct for that concrete input. So essentially, we're checking that the compiler ran correctly that one time, which is not the same thing as actually verifying that the compiler would be correct for any input. And you know, what you would really want to do is verify that the compiler is correct for any input. And so that's what we did in this project. So we opened up one of these compilers, one of the ZKP compilers, in particular one called CirC that we built here at Stanford, and we looked at just one pass in that compiler, which is called the Finite-field blaster. This is one of the last passes in the compiler. It maps some kind of intermediate representation over Booleans, over fixed size integers, over field operations to just field equations. So in some sense, this is like the most field intensive pass in the compiler. And our goal was to verify that this compiler was correct. This pass of the compiler was correct once and for all. And it turns out it's a somewhat challenging thing to do, in part because this pass is pretty sizable. There's a lot of code in it. And essentially the reason there's so much code is for all the different kinds of Boolean operations or fixed size integer operations or field operations, there's a different rule for how to map that operation into field equations. And so, you know, there's like an operation for bit vector, i.e. fixed size integer additions. There's an operation for Boolean and, there's a rule for Boolean or, and so on. All in all, there's around 80 different rules. Because, you know, there's also rules for like how to add new variables to the system. Yeah, it gets kind of complicated. And so our hope was to come up with some verification strategy where we wouldn't have to analyze every single rule by hand, where we could automatically check all of the rules. And the way that we do that is by automatically, we write sort of a transformation that takes the code that defines the rules and turns that code into an SMT query that checks whether or not that rule is correct for a particular definition of correctness, which we show as the right definition. And so once we have this transformation, we can transform all of our rules into SMT queries, and we can pipe them all into the SMT solver and see what the SMT solver says. Is the rule good or not? And if all the rules are good, then we have some pen and paper proof that shows that the whole compiler pass is good as well. Unfortunately, we actually found that all the rules were not good. During the course of checking these queries, sometimes the solver found counterexamples. So we actually found bugs in 4 different rules. Most of these bugs are completeness bugs, which are less serious, but we also found a serious soundness bug in comparisons between fixed size integers. This is the kind of bug that if somebody had been using this compiler to build a private cryptocurrency, if they were using those comparisons to, for example, ensure that account balances are positive, this would have led to a solvency issue. So we were very happy to find these bugs and fix them, and now we know that the compiler pass is correct, which is great. The other thing I'll say is that the reason that we were able to do this effectively is because our compiler actually, you know, the compiler typically operates over 32-bit fixed size integers or 8-bit fixed size integers, but this compiler pass can work over fixed size integers of any bit width. It can handle fixed size integers of width 1, which maybe isn't so interesting, or width 2, which maybe isn't so interesting. But this was actually very useful for verification, because the verification problem, these SMT queries for really wide integers, is actually quite hard. The solver can't handle it. But the solver can handle the verification problems for very small integers. And since the design, the way the compiler pass works doesn't really depend very much on how wide the integers are, we were able to do the verification problems over integers of size 3, of size 4, and we were able to find the bugs at those bit widths. So having a compiler that could sort of scale to any size computation was very useful from the verification perspective. Okay, so I think that's all I wanted to tell you guys about. In short, I told you about an SMT solver that can understand finite fields. I told you about some work that we've done using this SMT solver to verify part of the ZKP compiler. And I also told you about some work that we did basically doing translation validation, so checking particular ZKP compilers on particular Boolean inputs. I hope this is interesting. The main reason that I came to tell you guys about this stuff is because we think that the solver should be useful in more contexts. And so I'll answer any questions that you have now to the best of my ability. And more broadly, if there's any context in which it seems like you need some kind of search engine over a space that's related to finite fields, I'd encourage you to come talk to us or try out CVC5. The field solver is available via all the APIs, so it should be pretty usable.
If nobody has questions, So just to recap the algebraic thing. So the equivalence between Grover-Bayes is that in the ideal there's the constant one. The equivalence with the satisfiability holds only on the algebraically closed fields. So that means if the one is inside even over the base field, we know where we are, it's fine. But if not, we don't know, and that's exactly why you were talking also about the field polynomials, right? So the field polynomials are the x to the p minus x, right?
Yes.
Exactly, and this is not feasible, honestly. So, which seems obvious because they're too high degree. So what is the strategy for this? How did you call it? This backtracking.
The backtracking search. Yeah.
Yeah. So is this easy just to give a hint here?
Of course. Yeah. I'll try to sketch it. So, and I realized I should have like brought the iPad so I could kind of diagram this as we go, but I did not. So it's a backtracking search. And so essentially what it tries to do is it actually tries to find the satisfying assignment. And it does that by fixing the value of one variable at a time. And if it gets stuck at some point, if it finds for the variables that it's the values it's chosen so far, there is no way to complete the assignment, then it backtracks. So that now the only remaining question is how does it choose values for variables? And so I'll give you a sense of that. There are basically just three rules. The first rule is simple. If there's a univariate polynomial in your system, then factor it. And that tells you all of the univariate solutions for that variable, and just branch on all of them, try them all. Second, if there isn't a univariate polynomial, but the dimension of the ideal, i.e., or really the dimension of the variety that the ideal describes, so the dimension of the solution space is 0, and you can compute the dimension from the Grosvenor basis, then there's actually a way that you can compute a univariate polynomial whose roots cover the multivariate solutions. This is called a minimal polynomial. And so we compute this minimal polynomial, we factor the minimal polynomial, we branch, we do exactly what we were doing before. But sometimes the dimension isn't 0. Sometimes the dimension is positive. And the dimension being positive is interesting because what the dimension being positive means is that the size of the solution space over the algebraic closure is actually very large. If you view like the system as being defined with integer coefficients and you take the limit as p grows, asymptotically the number of solutions is the size of the field to the degree. And so if the degree is positive, the number of solutions is asymptotically large in the size of your field. And so what we do in this case is we actually just guess. We guess random values for random variables. And the intuition here is that if what you are doing is looking for extension solutions, then very quickly you're going to find an acceptable guess. Of course, we're not looking for extension solutions. So this intuition, it doesn't actually explain what's going on here. And what we find somewhat intriguingly is that this algorithm does seem to do very well, despite the fact that we can't prove that it does well. And actually, I should say we can even come up with examples where it does very poorly. So we can cook up contrived systems of equations where this will go off the rails and it will never terminate. But the actual benchmarks don't seem to trigger this. And so that's sort of interesting. I think that essentially what's going on is that somehow the benchmarks that we have, the systems of equations, they're actually very constrained. They're so constrained that there can't be large numbers of solutions over the algebraic closure. Somehow most of the solutions are in the base field. And we're not really sure what that is. So we have a lot of questions here, and yeah, I would be very interested in talking more about this, and I can give you some of the formalizations of why we think this works that have failed, and some that haven't failed yet, and we're also very curious whether there's a way of improving this backtracking search to get worst case runtime that's sublinear in the size of the base field. We think it should be possible. There's we wouldn't be violating any we wouldn't be proving any surprising things about complexity. The runtime can be sublinear in the size of the base field, and this is still not a good SAT solver because the dependence on the number of variables is bad. So nothing really rules out a better solution here. We're just not aware of one. That might be more detail than you were hoping for, but hopefully it's helpful. Yeah, far more detailed. A simple question. So the solved instances means does that mean the number of field equations? It doesn't. Or the 600 in the
in the benchmarks?
Yeah, so it's the number of, so every benchmark is a Boolean formula and a system of field equations that putatively encodes it. So every instance is just a formula equation system pair. And how many, but it's a good question, like how many equations are there here? So what we actually control, so I'll talk first about, basically, so the number of equations varies from 10 to like 800. And the number of variables ranges from 10 to 800. And the way that we get that is that we actually sample Boolean formulas with a varying number of intermediate terms. The number of terms varies from like 1 all the way to like 128. And then we feed these through the compilers. And when the number of Boolean terms is something like 128, and many of these intermediate terms have like high arity, so they're like the and of like 5 or 6 things, you end up with several hundred equations. Let's see, anything else I should say there?
So,
I guess
sorry, just the last question here. So, and that's sufficient for proving, say, I mean, if I consider just rank 1 CS quadratic equations for integer comparison or something like it, depending, of course, on the integer size, I remember that I suppose there were much more constraints to be set here. So at what scale did you find the bug in that software, in that CirC? How's it called? CirC?
CirC, yeah. So yeah, this is definitely not powerful enough to throw it at a real R1CS system, wholesale black box and find a bug, because most meaningful rank 1 constraint systems or Planck circuits are going to have on the order of like 1 million equations, not on the order of like 100 to maybe 1,000 if we're being generous, which is kind of what we're dealing with here. But our hope is that what you can do is you can build some kind of compositional verifier that reasons about the large constraint system, subsystem by subsystem. And that's exactly what would happen in the case of verifying CirC. So in the case of CirC, we were able to verify rule by rule that the compiler was correct. And verifying that each rule is correct requires reasoning about some constraint system, but that constraint system has on the order of hundreds, or in some cases, for simpler rules, even tens of equations. And we're not the only people who have been doing that. So there's a company, Veradice, that sells ZK audits, and behind the scenes, the way that they do the audits is they have a bunch of automated bug finding technology. They also build automated bug finders that are compositional. They try to reason about these systems one piece at a time. And then they use the solver as a backend for reasoning about every sub-constraint system. That said, compositional reasoning is like, I mean, there's lots of ways of doing it, and finding the right way of doing it for different systems is, a big problem and depends a little bit on the system.
Thanks.
So when you do this backtracking, is it crucial that you do the Gröbner bases before? Like, is that a requirement?
It's not a hard requirement. That's a really great question. The only thing in the backtracking algorithm that requires the Gröbner basis engine is computing the dimension. You could imagine like variants of the backtracking search where we don't need the dimension, where we try to estimate it, where we like try to compute certain minimal polynomials and just give up if we seem to be failing. You could also imagine breaking the system into like subsystems that don't interact with each other very much and computing Gröbner bases just for the subsystems, and then doing kind of coordinated backtracking search where you're looking for a joint solution across all the subsystems. There are lots of options here. And what we have found in practice is that the Gröbner basis engine seems to fail more often than the backtracking search fails. And so we're very interested in relaxations where you don't have to compute a full Gröbner basis.
Because that's probably that should be the bottleneck now, right? In your algorithm, or
the backtracking search has runtime that's worse than the Gröbner basis engine, at least in the worst case. But somehow empirically, it seems like we have a hard time coming up with we have not run into any real examples where the backtracking search fails, but the Gröbner basis engine succeeded. We can cook up contrived examples, but we haven't found real ones. I'm gonna actually back up to like the future work that I skipped, just to give you like one example of a situation where the Gröbner basis engine fails. So if you have like bit constraints, which are super common in ZKPs, This is actually a situation where the Grosvenor basis engine really struggles.
Hmm.
So just this constraint system that I've written on the bottom, you've got variables b0 through bn, you've constrained them all to be bits, and then you have the fact that their sum is equal to x. And if you make some statement like, find me, x equals 17, find me the bits, the Grosvenor basis engine will find the bits for you. But it will take it a very, very long time.
Right.
And so we're very interested in, for these kinds of things, what we've been thinking is that what we actually want to do is build some kind of ILP solver into the field equation solver and try to reason about these bit constraints, not as bit constraints, but as ranges. And we've had some luck with that in some situations, but we're definitely not at the point where we have a general purpose solution that we can put into the solver yet.
Mm-hmm. I have one more question. Maybe it doesn't make sense, but like somehow you want to avoid the field polynomials because, right, you imagine working over a very large prime and then it's just too big. But what I'm just wondering is that, like, imagine you want to verify your system of equations that you have, and ideally you want to verify this over this huge field. Would it make sense then to first verify it over a smaller field? Because usually, I guess these constructions, they wouldn't depend so much on the prime, I suppose. Maybe I'm wrong about this. I'm thinking.
No, you're right. So it doesn't always work. So changing the field can change whether the property holds or not, and there are some compilation techniques that do rely on properties of the field size. So like a great example is right now the best compilation technique for compiling an XOR is to add up the inputs, like a high arity XOR is to add up the inputs, do a binary decomposition, and then take the ones place. And if the addition overflows, then suddenly this doesn't work, right?
Yeah.
But you're totally right. Like most of this stuff doesn't depend on the field size at all, and a lot of it, even like that XOR thing, as long as the field doesn't get very small, it's fine. And so doing some kind of field change seems totally reasonable. And it's not something that we've explored yet, mostly because we're not sure how to like figure out automatically when it's equisatisfiable to change the field size. But I think that's really promising, and I hope that somebody looks at it.
Thanks. Makes sense. Thanks.
So Douglas has a question. Is there any connection between this work and the symbolic verification of ZK? So if you think about like symbolic verification as like building like a symbolic execution engine, is that the sense in what you mean that? Or is what you mean like the people at like University of Saarland who do like symbolic verification of crypto protocols?
Hi. So I'm talking about the verification of the security properties of a protocol. Let's say a protocol built from ZK, and that kind of symbolic verification.
Yeah, so I think you're thinking more like SymX. Yeah, so this kind of solver is like it's the foundation on which you can build a SymX engine. It's not the whole SymX engine, like but it's part of it.
Okay, yeah. Thank you.
And indeed, like as I was alluding to, the folks at Veradice who build tools for this, they have something like a SymX engine. That's one of their tools, and it builds on this.
Okay, do we have any other questions? It looks like no. So I'd really like to thank you, Alex. So really fascinating topic. Yeah, it's a.
Well, I want to thank you guys for tolerating the sort of change of gears moving into verification. It's yeah, it was I imagine it was quite the shift, and you guys were a great audience.
So thanks a lot, and see everyone next week.
Ciao.
See ya.
Bye.
Actually, I had a system question I wanted to ask you, James.
Sure. Yeah.
Is Camille still around?
Yeah.
Oh, good.
We're sort of split at the moment because, I mean, we're expanding and we're having a whole new office being built. So he's
I know, I
moved-
heard. Yeah, all the cryptographers got kicked to Sontingbert, right?
Yeah, that's me.
Yeah.
But yeah, even there we're in a couple of different offices, but yeah, he's got a group here.
Cool.
Actually, yeah, I was going to start working on a well, I wanted to do a little sort of MEV side project with him, but I don't know if he has time. So
Yeah.
Yeah.
Cool. Right on.
because yeah, he was there last year, was it? Or
Yeah, and I actually I was in Saarbrücken last summer for a while, just
oh, cool.
mostly for fun. So
Well,
Right,
I'll tell him you said hi.
yeah, please do.
Cool. Okay.
Okay.
Well, thanks for a great talk.
See you guys.
Bye.